Thank you very much for joining this time's webinar. So my name is Cyprian and I'm the International Technical Manager for Midas NFX here in South Korea. So we are broadcasting in live from South Korea, and we have a lot of people, a lot of engineers who joined this session today. Because this is a new webinar that we never did before about the analysis of the flow inside the rotating equipment. So very interesting topic. I just finished the presentation, so I hope it will be interesting for you. So let's get started. As usual, if you have any question during the presentation, just ask. I'm not sure I will be able to answer directly, but I will answer everything at the end. So this is what I will talk about during this webinar. So first I'll do a short introduction. I'll talk about rotating equipment analysis and the advantages and disadvantages. Also, the sliding mesh analysis method. I'll show you a demo of how to simulate a 2D fan using the sliding mesh. And then I'll talk about the moving reference frame, also called MRF method. And I'll show you also a demo of a stirred tank analysis. So a lot of things to do. So let's start. So first of all, you must understand why we are doing such kind of analysis. So for most of you, it's obvious, but the purpose is that we want to evaluate the performance of rotating machinery. So it can be pumps, it can be fans, it can be a lot of rotating equipments, and also evaluate the security, for example, of the blades. So what you can do is do a rotating analysis using the techniques that I'll show during this webinar. And after that, you can perform a structural analysis using the fluid structure interaction feature to get the pressure on the blade and analyze the structural model of the blade. So actually, how do you simulate these? So this is the topic of today. How do you simulate that? Well, if you think in a normal terms, you would simply mesh everything, apply a rotation to the pail, and hope that it solves. Well, it's not exactly like that, because if you do that, the rotation is quite huge, so the mesh element will become distorted, and you cannot get anything from that. So we have actually two methods that are used to simulate this kind of analysis. The first one is called the sliding mesh method, in which the mesh elements are put into rotation. And then we have the second method, the multi-reference frame method, also called MRF. Now, what are the advantages and disadvantages of those two methods? So first of all, sliding mesh method is used for very detailed simulation in real rotation condition. And disadvantages are that you require a huge number of elements. It requires transient calculation, and also you need the accurate rotation information. So generally this is used when you want to analyze the performance of an impeller or a fan, and you really have to model this impeller and all the blades and everything. So it's used in this case. Now the MRF method is much faster than the sliding mesh method to solve, because mostly it's using steady state calculation and imposed velocity. So I'll present right after how it works. The small disadvantage that you have sometimes is that you have to perform for several initial impeller position, because this is static analysis, so your impeller will stay static in the fluid. So even if you simulate the rotation, I'll explain. And this is used when you want to know the flow pattern in the steady state in the system. So for example, if you analyze a tank and you want to know what is the flow pattern, you can use this because you don't focus on the blade or in the performance of the impeller, but on the flow. Now let's talk first about the sliding mesh method. So sliding mesh method, so to tell you very shortly what it is, first of all, you create a fluid area around the impeller. Then this impeller rotates at a certain speed. So it really rotates. It means that it's not a fake rotation, it's a real rotation. So the mesh set will rotate. And the fluid information, the pressure velocity between the rotating mesh and the other static mesh set will be exchanged through contact. So it can be sliding contact because it slides. So basically, yeah. The thing is that it uses transient CFD analysis because your mesh set is really rotating. So you are really simulating as if you were in real rotation condition, the rotation of your impeller. So transient CFD analysis has some disadvantage if you're only interested in the steady state. Disadvantage is that it requires very small time increment, very small mesh, so the model should be built very carefully in order to get correct results. Now I'll show you a very simple example of how to simulate that on this model. So this is a 2D fan that I will try to simulate using this sliding mesh. So let's switch to Midas NFX. So here it is. Now let's start the simulation by creating a new project. So this will be a 2D project. So I check the 2D option. And I will import my model that I prepared. I will try to go slow because sometimes with the connection it tends to be slower. So we'll hide all the guiders. So if you look in the walkthrough, you see that I have two geometric shapes. I have the impeller and I have the body around the impeller. So the first thing I have to do is to create a material. So in my case, I will create a water at 25-degree material. So I just select it in the database like that. Second thing, I'll have to define a property which corresponds to that. So in case of sliding mesh, I don't need to define any other thing in this. You're sure that for the MRF I will use this moving reference frame, but here I just use that. So I click OK, and oh sorry, it's not 3D, it's 2D. I'm in 2D fluid conditions. Okay. Now let's define the condition for the CFD analysis. So I go in the CFD tab, where you have all the types of boundary condition that you can apply, and I'll define a simple outlet to this edge, and the velocity will be 1 meter per second. The outlets at this edge will be pressure 0. Now I'll have to create a wall around this. And for this wall, this will be a dimensionless wall type. So if you watch the previous webinar that we did, you probably understood why I'm using the dimensionless wall. If you didn't watch this webinar, the webinar video is available on the website, so you can watch it again. So let's apply this. Now what I have to do is to apply a wall to the impeller. So okay, you have to apply a wall condition to the impeller. And so basically this is also dimensionless wall, but I will apply the motion control to it. So this is the condition you have to create to basically tell the software that you will use the rotation of this. So I will create a rotation motion, and I'm selecting the mesh deformation tab. So it's when you use sliding mesh, this is the same mesh deformation. So check that. The body mass is fixed, and I have a rotation in Z direction. So I'm checking the rotation, region motion, and here I have to create a function to assign the rotation to this. So let's call it rotation, and this function has to be in degree. So the value will be 3000 degree per second multiplied by t. So I'll explain later why I'm using this value, because probably some of you are wondering that. So okay, so you select this function, I click on OK. Now that I created my motion, I just assign it to this wall, and I click on OK to assign that. So now I assigned the external wall and the moving wall, and I have to create the contact between the two parts. So I'll just go here and open the manual contact. So it's an edge-to-edge contact fluid. Let's hide this part, and like that, activate again. Now I have to create a contact parameter for CFD. Click on OK, and I have it. So you can view this contact here in the worktree. Okay, now I'll have to mesh all that. So I will apply first a size control on the impeller. The mesh size will be 0.001. So I will hide the boundary condition. So okay, so now you can see. So the size seems okay. I'll show you a bit after how you can calculate this size. Is the video okay for everyone? Because I have a question telling that the screen is pausing. So can you just tell me if everything is okay up to now? Okay, so seems okay for other people. So I will continue. Okay, so I created the size control, and now I will mesh this. So I'll go in the 2D mesh, select the impeller, and I have to, okay, the properties, there's only one property. So the mesh size will be 0.002, so basically 2 millimeter. And I click on apply. So you see that the mesh is really fine. So this is what I wanted, and I have a small gradation up to that. So now select the body, and here it's very important to uncheck the option merge node, because I have a sliding mesh. So if I merge the node together, it will not be able to rotate. Okay, so I created the mesh. So now that I have done that, the only thing I have to do, there's one thing additional that is very important actually is that you have to check the orientation of the elements. So this is special to 2D type of modeling for that rotation, because if the elements from this face are not in the same Z orientation than the body, you will have some problem during the simulation. So let's activate here the show height element thesis, and you can view the orientation. So look on the side like that, and as you see, the elements from here are not the same direction for the Z axis than this area, so I'll have to change that. I go in mesh parameter, 2D, change the coordinate system, and I will select the body mesh set and reverse the normal axis. Okay, now everything's fine, so I unactivate that. Another additional thing that I'll do is that I want to know what will be the calculation of the velocity and the pressure during the analysis. So I will define a monitor condition. So I go here in the result for the total pressure at certain position. So I can select a node. So let's select 2 nodes like that. Click on OK, and it will monitor the pressure and velocity at this point during the analysis. So very useful function. So now that I did all that, my model is ready. So I just have to create a transient CFD analysis case and set up carefully the options here, which are very important. So the time increment should be very, very small. So I'll tell right after how do you calculate that, because this is a question I get very often. And sorry. So I define it like that to 0.0002 second, which is very small indeed. I will put like 200 steps and max iteration 3. And I think it's okay. So now I can run the simulation. So let's so simulation will begin. So now you have the graph which shows you the convergence of the analysis during the simulation. So this graph has to converge to a number which is lower than this value. So you have to wait, so the value is going lower, and this shows you that you have reached the convergence. And here in this window you see that you have converge, converge, converge. It means basically that the model is correctly defined and that you are getting the correct results. So in case of non-convergence, it will oscillate like that, or it will go up, but you will not reach a stable solution like that. Now let's look at the result of the points I'm monitoring right now. So here you have the different, you can view the different values for the velocity and the pressure. So during the analysis it's automatically updating. So I don't want to wait, so I'll open a model which on which I finished the calculation. So here it is. So now here you see that you have the rotation of this. So you can view the animation like that. and I succeeded to make my simulation. So this is it. So basically, if you want to do that in 3D, the only thing you have to do is to change this model in 3D and apply the same process. Just one thing additionally, I think in this model that I just solved, I forgot to do one thing. I forgot to activate the mesh deformation module. So if you want to have the rotation, you have to activate that. So I'm just telling that in case you will look at this video later on and you will try to do that. Okay, so now let's come back to the presentation. So now the question that probably some of you are having now is first, how can I assign the rotation function? So a lot of people are asking that. You saw that I created a function for the rotation 3000 multiplied by t. So how do I calculate that? So very simple. The function total is in degree. So the x that you input here is in degree per second unit. If you have the RPM value, you can simply convert this degree per second in RPM and you will get the value. So if you are having RPM, you have to convert that into degree per second and multiply by t, and you will get the function for the rotation. Now, a question which is a bit more advanced is, how do I know the time increment I have to use for this analysis? I was telling that you need a very small time increment, but this is pretty vague. So how do you actually know which is the time increment you need to get the convergence? There is a number called the CFL number, current Friedrich-Levy condition. So this is the definition from Wikipedia. So this is a dimensionless number, and the magnitude of the velocity, so u is the magnitude of the velocity, delta t is the time step, delta x is the length interval, and basically Cmax is a constant. So here, if you read that, it's telling you that the value of Cmax change with the method used to solve the discretized equation, and especially depending on whether the method is explicit or implicit. So you can set up Cmax equal to 1 if you're doing explicit, and if you're doing implicit, solve are less sensitive to numerical instability, so you can use a larger Cmax. So in this case for CFD, you should use Cmax equal to 1. So what I did is that I put Cmax equal to 1 and I get an equation like that. Delta t is smaller or equal to delta x divided by u, the velocity. So the first thing I do is I measure the mesh size at the area where I would have the maximum velocity. So in this case, I know maximum velocity is around the blade. So the mesh size around this area is 0.001 because this is the mesh size that I defined, and divided by u. So here u is defined in radian per second. So you have to convert the RPM into radian per second. So it gives like a value of 52.3 radian per second. And finally, you get a value of delta t, which is inferior or equal to 2.3 power minus 5 second. So this is why I used this value to calculate. So very useful equation that I hope this will be useful for you. Now we are going to the second part of this webinar today, which is about the moving reference frame method, also called MRF. So now, instead of rotating the impeller like we did at the beginning, The MRF is a bit different. It applies an opposite velocity on the rotating frame. So the two conditions are actually the same, but when you look in the perspective of the relative speed, so you can look at this photo, for example. When you are doing simulation in the wind tunnel of on a car, the car is static, so it's not, and you look at the impact of the air on the car. So in this case, you can think this is the kind of thing that is done when you are using MRF. So of course it's a bit more complex than that, because actually you have rotation, so you have to consider centrifugal force and Coriolis acceleration and other things. So Midas is taking that in account. But basically this is like that. So when you do sliding mesh, you have real phenomenon, so you simulate the rotation. When you do MRF analysis, you are actually simulating the air rotating around the blade, which is fixed. Okay, I have one question from someone who is asking in the previous example how I can get the torque from the analysis. So you can get the torque by analyzing the pressure on the blades. So once you do the analysis, you can you have an option to investigate the pressure which is created on the blade, and this basically gives you the torque after you have to calculate it and like that. Okay, so what is MRF? So I was talking about that. So more simply, multi-reference frame method computes the fluid flow using both the rotating and the stationary reference frames. So you can think that it's as if you were standing in the rotating zone, not moving, so fixed in the rotating zone and fixed in the stationary zone, and you have like that two referentials. So here you have a stationary reference frame, and you have the moving rotating frame, and the two frames are linked together with a simple equation, u relative equal to u minus rotation multiplied by r. So rotation vector is defined as the product of the rotation axis and the omega rotation velocity, and you get the relative velocity like that with this equation. And then by plugging the relative velocity in the governing equation, you get the following equation by plugging the rotational velocity in the momentum equation, and this is the final equation that is solved. So this is the rotational force in the direction of J. And now I'll show you a second example of how to simulate a steered tank with baffles using this multi-reference frame method. So let's go into Midas NFX. Let's close the previous model. So if you see something in Korean, it's normal. It's because my computer is in Korean. I'm telling that because sometimes people are freaking out. Okay, so here I get, this is the model that I just imported. Let's hide the guiders. And let's show the line only. So this is my model. So let's take a look. So I have two parts. The first is the outside flow, and the second is the rotation area with the blades. So how do I simulate this tank? So this is what I'll try to show you right now. So first of all, I create a material. So like in the previous example, I'll just create a fluid material with fresh water. And I create a property. So 3D property, CFD. So here I have to create two properties actually. One property that will be assigned to the external mesh element that will not rotate, and one property for the mesh set here that will rotate. So actually the fluid will rotate, but not really the model. So let's create water. So this is my first property, which will not consider the MRF, and the second I will call it MRF area. And here I have to activate the moving reference frame. So you see that you have to define the origin and the direction. So direction is Z direction. The angular velocity is 250 RPM. And I click on OK to generate the two properties. Now, now that I did that, there's something that is important to check because in this analysis, the two mesh sets will be connected with nodes. So when I do the meshing, I will merge the nodes together. So I want to be sure that the faces between the two models are connected together. So to check that, I have a function in Midas NFX called check duplicates. So I click on this function and I click on apply, and now if you see some orange faces in orange, it means that the faces in orange are connected together, so it's okay. If you don't see anything, it means that there's a problem and you have to connect this model. So how do you connect that? There's a function called auto connect, so this is the most simple option. Otherwise, you can also use the Boolean operation to connect the two parts together. So I'm telling that because sometimes people have complex models and I don't know how they did that, but the parts are not connected together and then there's a problem to merge the nodes. So now that I did that, let's mesh all that. So let's mesh first this area. Sorry. Okay. So look on the side view, and I will go in the mesh tab to apply size control on the impeller. So let's change to a selection in a circle like that. Okay. And the size 0.004 meter. Apply. So I control the size on this impeller. Now I control also the size on the baffles. So let's select the baffles and use a linear grading. So starting length will be 0.004, the end length 0.012, and I'll use a symmetric seeding, and this is what you get. Okay. Now I'm ready to mesh. So the first thing I'll mesh is the central area. So let's choose 3D mesh, select that, and the mesh size will be 8 millimeter, so 0.008. I'm using the high-speed tetra mesher. So when you're in CFD, you have to use tetra elements. You cannot use hybrid. Also, you cannot use high order elements, so sometimes people are doing this mistake, so this option should be unchecked. So, and here property is this one, MRF area, because this is the rotating part. So okay, so now I created the mesh on this part. Second, now I'm created the mesh on the outside fluid. So the mesh size will be 12 millimeter. This time the property is the second, the water property, and I have to match the adjacent faces. So what this feature is doing is that it will match the mesh nodes on the external fluid and on the rotating fluid. And then I have also to check the option merge node, so it will match them and merge them together, because if you don't merge them, it will not work. Okay, so I did that. I click on OK. I wait a few seconds. So now I just generated my my mesh for that. So let's take a look just to see if everything is in order around the impeller. So I think the mesh is okay. So as you see, the mesh is much more coarse in this case than in the previous sliding mesh case. And this is due to the fact that I'm doing MRF analysis. So I don't need, I'm in static analysis, and I don't need to consider so small mesh. Someone is asking, is there a theory for choosing the sizing? Well, you can use the same theory that I showed in the previous slide, but it comes also with experience. So you have really to choose. You have to refine the measure on the parts where you want to get more accuracy. You cannot, mesh very small everywhere, otherwise you have too much elements and it will be difficult to compute this analysis. So you have basically to find a way to be the most efficient possible. But generally, here in this example, of course, I know exactly what kind of mesh size I have to define, because this is a tutorial. But in a real project, you have to experiment with the model, and you have basically to start with a coarse mesh model, and then to refine the mesh in the areas where you think you need more accuracy until you get something nice. So generally, this is the way to go. Okay, now the next thing I have to do, so I created the mesh, I created all that, so I need to assign the CFD boundary condition to this. So let's hide the mesh, let's hide the labels. I'll display that in line only. Okay. Now I have to apply the boundary condition. So the boundary condition, the first one is to apply a wall around this rotating area. So I select again the impeller. This is again a dimensionless wall. And here I have to apply also the motion control to the wall. So like I did for the previous example, but this time it's not mesh deformation, it's rotating frame. So I activate it here. The origin is okay, and the direction is Z, and the angular velocity is 250. Okay. Now I defined the wall around this. Second thing, I have to define the wall around the model. So the final wall, the external wall, sorry. So I'm selecting all the faces except the top faces, because the condition for here is a dimensionless wall, but the top face will be inviscid. Okay, so now I have almost everything. So my model is totally defined, so I can save it, for example. And I have to create an analysis case. So this time I'm using Steadystate CFD, so I'll have much faster results. But of course you cannot compare with the previous example, because previous example was 2D, so it was relatively fast already. This example is a 3D example, so it will take a certain amount of time. So I will actually not calculate that now, otherwise we'll be here for 1 hour more. So in this case, I don't need to activate the advanced module. The time increment of 0.1 second is okay. Actually, in Steadystate CFD, this time increment is not really important, so you can leave it like that. It's important only for transient CFD. I can increase the number of steps. Okay, click on OK. OK. And basically my model is okay. So I can also define a monitoring condition and everything, like I did for the previous model. And now what I'll do is I simply open the model that I calculated previously to show you the results. So here I have the final results. So here too I didn't calculate everything. I didn't stop at the last increment. So this is so we don't see much, so I'll use a clipping plane. So here you have the rotation of the blade, and if I look at it in Z direction, you can investigate here the rotation of this part. So you see that it's as if it was rotating, so you get the same distribution, but it's actually static. And this is the MRF analysis. So the fluid is kind of rotating around that using the property and the wall, which are rotating in opposite directions, and it's creating this analysis. So much faster than if I wanted to do that using the first sliding mesh method. Okay, so now let's come back to the presentation. So actually this webinar is finished. So I'll tell you at the end how to find more training materials, so you can learn more about that. So first of all, you can get on our website, midasnfx.com. You'll find the tutorials in the tutorial section. So we have much more things now. This is an old screen capture that I took a few years ago. So this is an example of the tutorials you can find. There's a lot of tutorials for CFD as well. You can register for the latest webinars. So the next webinar we'll do will be the 10th of December. It will be the analysis of the interaction between fluid and structure, FSI analysis. So this will be also first time we'll do this webinar on FSI. So this will be probably a very interesting webinar, so I hope you will join it. And you can, if you don't have Midas NFX, or if you are interested to try it, you can go on our website and download a fully functional version of the trial for 15 days to test everything. And also I wanted to tell you about this new interactive tutorial center that we just opened. We are making lately a lot of interactive tutorials that you can test directly in your browser. So you don't even need to install the software, you can directly test that. So we made here in the menu interactive tutorials, and we regrouped together all the tutorials we made. So if you want to follow up that before downloading the trial, for example, you're welcome to try it. So now this is almost over, but I'll be answering the questions here. So please ask your question, and I will take a few minutes to answer them. Okay, someone is asking if NFX supports Windows 10. Yes, it supports Windows 10. So I hope this webinar was interesting. As I was telling, this was the first time I did this webinar, so I didn't know if this was exactly what you wanted to know, or if there's more things. So if you have still some questions or everything, you can always send me an email, and for the next webinar we will improve a bit and include more things inside. So the webinar will be available, the video will be available. So after I finish this video, I'll upload that, and this will be on the website on the recorded webinar section. And probably I'll also send you an email with the link of this video. So if you want to watch it again or watch the tutorials and everything. And if you want this tutorial model, it's not available yet, so you can just send me an email and I will send it to you. So my email is, in case you don't know, Cyprian at midasit.com. So I just wrote it in the chat section. Do you have any more question for today, or is it okay? Okay, I think there's no more questions. So thank you very much for joining. I hope you enjoyed the session, and let me know if you have more things to say by email. Goodbye and have a nice day.